In the previous video, we showed that every convergent sequence is Cauchy. Therefore, if a sequence is not Cauchy, it's not convergent. And in this video, we're going to look at some examples of proving that certain sequences don't converge by showing that they're not Cauchy. So, if a sequence is not Cauchy, then the sequence does not converge. So here's an example, a famous example of a sequence that does not converge. So we define the harmonic sequence to be the sequence defined by a sub 1 is 1, and a sub n is a sub n minus 1 plus 1 over n for all n greater than 1. So the first few terms of the sequence are a1 equals 1, a2 is a sub 1, so that's 1 plus 1 over 2, a sub 3 is a2, which is 1 plus 1 over 2, and then you add 1/3, etc. So a sub n is just 1 plus 1 over 2 plus 1 over 3 plus dot 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 plus 1 over n. And I claim that the sequence does not converge. In other words, it diverges. This is a very famous sequence. So one way to prove this is to prove that it's not Cauchy. So how do we show that something is not Cauchy? Well, remember, to show that a sequence is not Cauchy, we want to show that there is some epsilon greater than 0, such that for every positive integer, capital N, there exist integers m and n greater than capital N, such that the distance between a sub m and a sub n is greater than epsilon. That's what it means to not be Cauchy. So first, we'll observe. So what you want to do, basically, to show that something is not Cauchy, is you want to find some lower bound of the distance between a sub n and a sub m for certain n and m. And you want it to be some positive constant that doesn't depend on n. And then the idea is to pick epsilon to be less than that constant. So here's an example to illustrate that. So first, let n be greater than 1. Actually, let n be any positive integer. So it turns out that the absolute value of a sub 2n minus a sub n is greater than or equal to 1/2. Let's explain why. By the way, it's hard to come up with this, but once you see the proof, you can kind of see where this comes from. So the reason is, this is because if you look at the absolute value of a sub 2n minus a sub n, this is going to be, so you take a sub 2n means you go out all the way to 1 over 2n, right? And then a sub n just goes out to 1 over n. So then the difference is just what's left, which means the sum of 1 over n plus 1 plus 1 over n plus 2 all the way to 1 over 2n. And these are all positive, so I don't need the absolute value signs. And then the point is that each of these, 1 over n plus 1, 1 over n plus 2, are all greater than or equal to 1 over 2n. So these are all greater than or equal to 1 over 2n plus 1 over 2n, and then plus 1 over 2n. Now, how many terms do I have? I have n, right? I have n terms. So then this is equal to n times 1 over 2n, which is a half. So we've shown that every positive integer, n, has the property that a sub 2n minus a sub n is greater than or equal to a half. Now, how does this show that the sequence is not Cauchy? Well, let epsilon be anything less than half that's positive. So, for instance, 1/4, but actually any positive number less than half will do. Okay, so we picked this epsilon, and now we claim that for every for every positive integer n, you can find integers greater than n that have the property that the distance is greater than epsilon, or greater than or equal to epsilon, right? Because we just take a sub 2n and a sub n. So let capital N be any positive integer. Then the absolute value of a sub, okay, in the definition that I gave of Cauchy, your little m and little n have to be greater than capital N. So let little n be any integer greater than capital N. Okay, so you take capital N plus 1. And take little m to be 2n. Then the absolute value of a sub m minus a sub n, that is just the absolute value of a sub 2n minus a sub n. Well, by what we've shown, this is greater than or equal to a half. And so that's greater than epsilon. And that proves that the sequence is not Cauchy. So therefore, the sequence is not Cauchy, and hence not convergent. So this is a proof that the harmonic series diverges, right? The harmonic series being the sum of 1 over n from 1 to infinity diverges, because this series is really the limit of the partial sums, right? But the partial sums don't approach a finite limit. Okay, so that's a classic result, and this gives an example of how to show that a sequence is not Cauchy. And notice, by the way, that if you look at the successive differences, if you look at, so I'll just end with this final remark. If you look at a sub n plus 1 minus a sub n, that's just going to be 1 over n plus 1. Now that approaches 0 as n goes to infinity, right? But this sequence is not Cauchy. So being Cauchy is stronger than just saying that the successive terms, the successive differences approach 0. So it's not, being Cauchy doesn't mean that if you have, a1, a2, a3, a4, that these differences go off to 0. That's not true. You basically need that for past a certain point, okay, like a sub m, and no matter what term you have, a sub n, that these differences go to 0. That's basically what it means to be Cauchy. So it's not sufficient for just the neighboring, the a sub n and a sub n plus 1 for the difference of that to approach 0. It needs to be for all little m and little n greater than capital N.